Okay, in this lecture I'm going to continue talking about state feedback. So in the previous lecture I talked about the introduction of state feedback, I talked about the structure of the state feedback, and there's some of the properties of state feedback in terms of controllability, observability. So the question they posed in the previous lecture is, how do I design my control gain such that I can assign my eigenvalues of the closed loop feedback system? Okay, so in this section I talk about how we design the control gain, and what are the principles we typically use to design the control gain. Okay, let's go back to the previous the setup. We have a linear time invariant system given by x dot t, which is axt plus but, and yt is cxt. That's original linear time invariant system. And we have a state feedback control given by ut, which is rt minus kt, kxt. So this is called state feedback. Here's a property in terms of if we can design a control parameter control gain such that we can reassign the eigenvalues of a minus bk, because that's the goal we want to do. We want to assign the eigenvalue of a minus bk such as the system is stable, for example. So what conditions is sufficient to guarantee that we can design this case such that a minus bk can be arbitrarily assigned? So this is the condition. If my original linear time invariant system here given by star is controllable, or also people say is A and B is controllable, by using the state feedback given by the star, so the eigenvalues of A minus bk can be assigned arbitrarily, provided that the complex conjugate eigenvalues are assigned in pairs. Okay, so this is what it means. So if this is controllable, which means if my rank of my controllability matrix is equal to the dimension of my xt, so which means this is controllable, right? So I definitely, if I want to give eigenvalues of this, I want the eigenvalues of a minus bk to be whatever eigenvalues, let's say -1, -2. I could also assign a complex conjugate eigenvalue. Let's say -1 plus I, -1 minus I. So that must come as a pair, right? We cannot just assign one of them. Then that's definitely doable. We can always find a k that can do this. Okay, this means I have this dimension is 4. Okay, then I can do that. Okay, as long as it's controllable, we're fine. Okay. Now how do I assign how do I determine these control parameters? Okay, now I'm going to show you how to do it. Okay, I'll show you an example how we do that. So let's say if I give you a linear time invariant system given by x dot t, which is 1331 times xt plus 10 times ut, which means this is my A matrix is 1331 is 2 by 2 matrix, and B is 10 is 2 by 1. Okay, it's a column vector. And my standard state feedback control is given by ut is rt minus kxt. Okay, so you have to make sure that if I can design k such that a minus bk the eigens can be randomly assigned, because I want to assign the eigenvalue somewhere, right? So let's say I want to assign my eigenvalue to be -1 and -2, because this is 2 by this state is 2, so I can only assign 2 eigenvalues. Now you cannot do that check if this is feasible. We first check if the system is controllable. If yes, we can definitely do this. If not, sometimes we can still do that, but it's not guaranteed. Okay, so in order to do this, let's check if the system is controllable. If yes, then we can definitely select a case such that using the state feedback control, the A minus bk has eigenvalues at -1 and -2. For example, this is goal. Okay, so let's first check the controllability. Okay, so controllability is given, matrix is given by B and AB, because this is only 2-dimensional case. So I have B and AB. So B here is 10, and A times B, if you do the product, is just 13. So here this column are independent, so the rank of C is equal to 2, which is dimension of xt, because dimension of xt is here. Dimension I have xt is basically is x1t, x2t, right? So which means it is controllable. If that's the case, we can, according to what I mentioned over here, if it's controllable, I can definitely find a parameter, control parameter k such that a minus bk, eigenvalue and a minus bk, whatever value I want to design. For example, here is -1, -2. The question is, how do I find this k? Okay. So the second step, I want to select k such that a minus bk has eigenvalues at -1, -2. Okay, meaning that I want this to be true. So before talking about what is dimension, we will first figure out what is the dimension of a k. Like, do I have a column, or do I have a row, or do I have a matrix? What kind of, that's important, right? Okay, so to verify this, the dimension of k, it must be the case that a minus bk is well defined, right? Because that's my, let's go back over here. Yeah, a minus bk must be well defined, right? So here a is 2 by 2. The dimension a is 2 by 2, which means dimension of a has to be the same as dimension of bk. My b is 2 rows, 1 column is 2 by 1. So my k must be 1 by 2, right? Otherwise the product won't match, right? Because the product is 2 will be just 2 times 2. It won't match the dimension of a. Okay, so which means the k has to be 1 row and 2 columns. Okay, so let's say k is just k1, okay, it's k2. Okay, so the first step we have to figure out the dimension of k. So k is, let's say k is k1 and k2, because that's the dimension we must have. You have to make sure that a minus bk is well defined. Okay, so it must be well defined. So let's say it's k is k1, k2, and I can compute the a minus bk. So a is 1, 3, 3, 1. B is go back here. B is 1, 0. Yes, B is 1, 0, and k is k1 and k2, as we already figured out, is 1 by 2. So do the product. This one keeps the same. The second one, do the product is 1 times k1 here, 1 times k2 is k2, 0 times k1 0, 0 times k2 0. So we have this one. Then put them together. This is a minus bk. So now it says compute the eigenvalue of a minus bk. So the eigenvalue is given by the characteristic equation. It's given by determinant of a minus lambda I times minus a minus bk. We set to be 0, of course, right? So the determinant is given by the determinant of computer. This is the inside one is a computer of this eigenvalue. The matrix is lambda minus 1 minus k1. This is lambda minus this guy. And this is 0 minus this guy will be minus 3 minus k2. And this is minus 0 minus 3 will be minus 3. And this is lambda minus 1, lambda minus 1. So this is set to be 0. If you compute determinant, will be just this product, the product of these two. It's over here minus the product of the off diagonal entries here. Okay, because minus cancel out, so I can do just minus 3 times the whole thing. Okay. If we do a little bit computation, we get a lambda squared plus k1 minus 2 times the lambda plus 3k2 minus k1 minus 8 equals 0. So that's one we have. Of course, we don't know the value here. We don't know the eigenvalue because I don't know what is the k1 and k2, right? But I know my goal. So my goal is I want to figure out the eigenvalues to be just at -1, -2, right? So with the goal, we know that. We know here is, hey, I have lambda has to be -1, -2, right? So what my problem is, what should be a k1 and k2? Okay. So before doing this, compute this. So what we want to see, what kind of form equation will give me 2 eigenvalues or 2 solutions that will be lambda 1 and lambda 2. So you can sort of see is okay. Let's do it. This is heavy plus and if we do lambda plus 1 and lambda plus 2, yeah, will be gone, right? Will be okay. So if I do lambda plus 1 and lambda plus 2, I know this eigenvalue will be lambda minus 1 and then lambda minus 2, basically, right? So if you do this one, then we have 2 eigenvalues, will be just exactly what we have. If you do the product, we have lambda squared, it has to be plus 3 lambda plus 2. Okay, that's what we have. Okay, because if I have this polynomial and set it to be 0, then my solution will be lambda 1 is -1, lambda 2 is -2, which are the two eigenvalues. So we just have to do is to compare, right? To compare hey, because this is lambda squared the same. If I set this value to be 3 and this whole value to be 2, now this 2 will be the same. Now I would get I could say lambda 1 here. Lambda will be just -1 and -2, right? If I would set the value, because the two equations are the same, which means the eigenvalue will be this lambda 1 and lambda 2. So by comparing these two, I can say if I let k1 minus 2 equal to 3, and 3k2 minus k1 minus 8 equal to 2, now I should have lambda eigenvalue a must be to -1, -2, right? Because that's the equation. This equation will be the same, and the solution to this equation will be just lambda 1 and -1, -2, right? So by computing this one, we have k1. If this is true, I mean k1 minus 2 is 3, so which means k1 5. And then for the second one, this condition, we have 3k2 minus k1 minus 8 is 2, which means 3k2 is, if to the right hand side is 2 plus 8, and also plus k1. So k1 is all given by 5, so it's 2 plus 8, 10, 10 plus k1, 5 is 15. So this gives this, which means my k2 also is 5, which means I have here, k here is what? 5, 5. So that's my the parameter for k. Okay, so this is the way how to find the parameter k. So let's go back a little bit how we solve find the right k. So the first step we want to check if the system is controllable. Okay, if it's controllable, yes, the dolphin is always true. You can always find the k for any eigenvalue as long as either they are just real or they are complex conjugated with appearing as a pair. That's okay. So the way you select, you find the parameters, the control gain k, is to first determine the dimension of a k, so you can assign the scalars. Let's say if it's 1 by 2, you have 2. If it's 1 by 3, you have 3. Okay, it will be different. Once you do that, you compute a minus bk. Try to figure out the form, the eigenvalues by using characteristic equation. Okay, over here. Once you figure that out, assuming we already know, we should know that the goal of assigning the eigenvalues, which means I know what I want to have. So you just build this. The key part is you build this lambda 1 minus whatever eigenvalue you want. You can do more if you want to have more, right? And lambda 3. You set to be 0, then you compute the same polynomial. And one thing you want to make sure is all the coefficients for the polynomials, they should match each other. Then you will be able to figure out what the parameter should select. So that's the key idea you want to use to figure out what parameter you're going to use. Okay. So other than this, of course, this is the way we can assign the eigenvalues. So one question you might have: what is the principle of selecting k? For example, can I assign my lambda of a minus bk to it's negative 10,000? Is there any problem with it? Or like negative 1,000, for example? What's the problem with it? Yes, you can assign that. The problem is there are some of the challenges to do so, right? So there are general two principles for selecting this k. The first one is you normally want to have eigenvalues of a minus bk have negative real parts. You don't want to have positive. You don't want the lambda a minus bk to be 2, for example, positive 1. The reason is if I do this, if I use the feedback control law, and this is the linear time inversive after using the state feedback law control. Now I guess this is my system, right? If you solve the solution, because this is also linear time invariant system, right? The solution will be xt equal to e minus to the a minus bk times t x0 plus integration from 0 to t e a minus bk t minus tau br tau d tau. So this is one we use. This is a solution for linear time invariant system, right? So if some eigenvalue of a minus bk are positive, now the problem is this guy. The norm is this guy, which means some value, some entry for this guy will go to infinity, which means your xt will go to infinity. This is not, it's like unbounded. The state will go to infinity. It's not desired. Okay. The second principle is, so typically the control input, you don't want the control input to be really big. Okay. For example, if you assign this one in this way, so typically means your k can be really big. For example, k, if I say it's k 1, for the previous example, if you want to assign the argument like this, your k1 may be like something like 10,000 and one whatever value is. K2 maybe is 5200. It's too big. When you do that one, this k is too big. So which means your control input is very big. So typically the control input is, if you want to have a bounded control input, this is a pretty small, less than a certain value, for example. Now you don't want to select too big, two negative eigenvalues, to be, let's say, two negative. For example, you do negative 10,000. You want to just negative, probably negative 1, negative 2, maybe, or negative 1, negative 1. That's good enough, right? Okay. Otherwise, the UT is too big. So in terms of implementation, that's not feasible. Okay. So lastly, talk about some application very briefly. Okay. So there are mainly two types of applications of this linear time, the state feedback, and you can also modify for different problems, of course, right? So the first application is about a regulation problem. So when we talk about when RT is given by 0, so you're going to regulate your output to be 0, basically. That's what I'll regulate. For example, if I consider aircraft cruising at a constant altitude at h0, and if we consider plane at altitude 0, the plane over here, this is the plane I'm talking about, at the altitude h0, this is altitude 0, this is altitude h0. If you consider this plane parallel to the altitude 0, 1 to be your XOY plane, which means you shift your XOY plane higher a little bit. So my goal here is just to regulate the aircraft altitude at 0. So if you have some of the linear system of the altitude, for example, I'm using, let's say, height. Let's say use x dot t is axt plus but, another y t is cxt plus dut. Actually not dut. Let's assume that my y is the altitude. Now you're trying to regulate your altitude to be 0. If you want to make sure that your aircraft cross at a constant altitude h0. Okay. The other one, more general problem, is called a tracking problem. For the tracking problem, we talk about we typically consider two cases. One is called when RT is a constant. For example, you drive your car at a certain velocity, constant velocity. Okay, that's a goal. It's called tracking problem. So my goal is to make sure that my yt will go to this constant value a as t goes to infinity. This is also called tracking of a step input. Okay, called step input. So if you have this, if I have this is my r sub t, and I want my y, so this is my y, I want y to sort of go to that value. Of course, you could have oscillations, like you could have something like this. Okay, we don't talk about transient performance, but a goal has reached that. Okay. What if this RT is not a constant? So the tracking problem is also called a servo mechanism problem. So which means you could have something like this. This is represent this case. You could have a reference. For example, you could have a reference which is a straight line. This is my r sub t, and my goal is to sort of track this one. So this is my y sub t. This is y sub t, call it y sub t. Okay, so this is called the tracking problem, also called a servo mechanism problem. For this one, the state feedback law, there's a more general case for that one. General state feedback law is given by this. So we're still talking about this linearized system, right? The LTI system, linear time invariant system. So originally the state feedback law is given by u sub t, which is r sub t minus kxt. Okay. Now here the more general state feedback is we have one more parameter over here, which is p. So this is a constant. Okay, so there's some parameters. There's some constant, a scalar, constant scalar values. You're gonna scale it up and down because, for example, why this is important? Because if you have this one, if it's happening like this, if this is t, let's say this is my reference is here as of t, and if we use this one, if we have, let's say if p is 1, let's say I use this p is 1, now my output is this, y is this. You have some error, constant steady state error, right? Over here this is the error, e sub t is defined by this over here. Now you have an error, so you could say, hey, I may want to do change a little bit. Let's say I want to change, say maybe p is 0.8. If I do change p of 8, I'm doing something like this. Yeah, give me 0, because you could scale up and down to make your parameter to make the tracking error be 0. So this is an additional parameter we can adjust other than p. So p is a parameter one design. This is designed for the eigenvalues of AMSBK for like stability purposes. Now the p will only be used in your eigenvalue because this doesn't affect the eigenvalue. This is a way to scale up and down. So make sure your error will be 0. So this value can be adjusted to reduce the tracking error typically, okay? But in certain cases, the p may not be sufficient, okay? That's why the linear state feedback, the general state feedback also has limitations in certain cases, especially if my reference is some huge increasing value. Like if this is minus of t, so you may not be able to track it. But this p maybe can help you to reduce the error. For example, if I select some p, probably I can do something like this. Can end up having it doesn't catch it, but it have a constant error. You cannot have increasing. If you change, let's say this is a p, let's say 1.2 for example, whatever, 2 for example. If you check a different p, let's say if I do another one, let's say p is, let's use a different color. Okay, let's say this p is just 0.5. You may have something like this. You do here. You cannot track it, so error becomes larger and larger and larger. So the p does play a role in reducing the tracking error. The tracking error typically defined by et, which is rt minus 1st. Okay.